Hey, so I've got a talk coming up with a Meetup group I'm part of, Retired Technophiles of Mainline. Um, so I wanted to record this talk, which is about ROS, or the Robot Operating System, for a couple of reasons. One, I just need some practice giving the talk. And the other thing is it may be useful, so I'll put it out on YouTube with my other videos as well. So sort of things I look at is, what is ROS, a little bit of history on ROS, the evolution of ROS1 to ROS2, and some example robots that are using ROS, and then I'll give some demos of using ROS and how I've used ROS as well. And first thing is, what is ROS? Like it says, it stands for the Robot Operating System, which is a bit of a misdemeanor. It's not really an operating system. ROS actually runs on top of an operating system, Ubuntu in most cases. So what is it? It's a set of software frameworks for robot software development. And going a bit more into that, I've got this little diagram here that came off the ROS site. It's made up of plumbing, tools, capabilities, and an ecosystem. So plumbing are the components that actually run on a robot you're putting together. So plumbing includes things called nodes, topics, messages, and the inter-process communication that's going on. Also, there's tools that ROS provides. So there's a CLI, or a command line interface, you can use to manage the ROS components. There's simulators, so you can simulate using a robot. You don't even need a hardware robot. There's various simulators available. There's recorders, so a lot of times it's useful to be able to record what's driving a certain node in ROS and being able to replay that recording for testing. And there's other things like RViz, which will show you the robot information. So telemetry coming back from the robot shows you that robot navigating, which makes it easier to navigate in a simulated environment. There's also some capabilities that come with ROS, or there's a lot of capabilities that come with ROS. Usually these are managed as packages, so there's capabilities around navigation. So a lot of times you want to be able to have your robot move from one location to another, and you usually want that to happen autonomously. So being able to tell the robot move to a certain location and have it be able to plan how it's going to move around the environment to the location. So that's part of navigation packages. There's map building packages. So a lot of times to do navigation, you need to have a map of the environment so the robot can plan where it's going to go and how it's going to get there. Frequently, the map building uses a LiDAR to map out the environment, and there's packages to do that. Also, there's packages for things like computer vision, speech, either talking to the robot, letting it accept your commands or have it talk back to you, and then hardware devices like LiDAR, other sensors, light sensors, environment sensors, proximity sensors. There's a whole bunch of them, and there's a lot more packages than there. There's probably hundreds of packages out there with different capabilities. And then finally, ROS is also an ecosystem, so it's a community. It's a lot of the packages are open source and available on GitHub, so people can work on packages and capabilities together. The primary location for ROS information is www.ros.org, and there's also a specialist community around industrial use of ROS, so companies like Siemens and Intel, a lot of the big ones, Google, Amazon, are part of the rosindustry.org, as well as Twitter feeds. There's YouTube's, a lot of YouTube videos about ROS, and there's meetups around ROS as well. The big one is ROSCon, which occurs yearly. So you can kind of see here is graphically shown how ROS is made up of all these four things: plumbing, tools, capabilities, and ecosystem. And I'm going to talk a bit more about the plumbing in one of the later slides. And the reason for ROS, so it enables more efficient robot development by not having or not requiring developers to reinvent the wheel. A big problem at the start of developing robots was everyone had to rework out how to make the robot move, do simple things like use cameras, use LiDAR, so a lot of that repeated code isn't needed anymore. And also sharing of common robot capabilities, so having a community that have a shared way of developing robot capabilities allows a lot of people to work on individual capabilities. And finally, it allows for the abstraction of the hardware layer, so you can use ROS on a lot of different things that are robots, or even things that don't look much like robots. Anywhere you want parts of a mechanical thing working together, ROS is useful. So I wanted to do a little bit, have a look at the ROS history, just because it's really interesting the way ROS came into being. So starting just before 2007, ROS initially was a graduate project of some graduates in Stanford University. They wanted some of the goals that I just showed about ROS, but we're just developing it as part of a graduate project. The next big thing for ROS was between 2007 and 2013. There was an incubator set up called Willow Garage. That was actually set up by Scott Hansen, who was one of the members of the initial Google team. He was the third member. By 2007, he's a billionaire. Again, he came out of Stanford, so was really interested in robotics. So he wanted to set up this, and the key thing here is not-for-profit incubator to investigate robotics. It was called Willow Garage. And some of the key enablers that were put in place that allowed Willow Garage to be a success was to base robot development on open source software, and picking up ROS, again because it came out of Stanford University, as the thing that was open sourced. So Willow Garage actually managed the ROS as open source between 2007 and 2013. They also managed other open source software related to robotics, things like OpenCV and PCL, which is the point cloud library software, all key things for robot development. As well, there was a community developed at Willow Garage around robotics. So there was a core robotics team, people coming out of university to run Willow Garage. And probably the key thing was the internship programs with graduate students, where people were brought in to work with the core team to develop robotic capabilities. And that helped advance and popularize the use of ROS, and especially in universities, as these interns returned to university, they sort of spread the word about ROS and what was being done at Willow Garage. And then finally, the thing that Willow Garage provided was hardware and the support needed for robot research and development. A couple of key robots that came out of Willow Garage is PR2, which we see here, which is kind of a humanoid-looking robot, had arms, a base that could move around, a lot of sensors, computer cameras and things on it. Very advanced robot, and also a robot called TurtleBot, and we can see it here. And both these things were also made available commercially, so as people moved back to universities, they could use these same robotic platforms as well. And I think there's another advantage of having someone like Scott Hansen, who could finance pretty advanced hardware for people to use for their robot projects. Willow Grove actually wrapped up in 2014. At that point, the ownership or the management of ROS as an open source project was moved over to OSRF, and a lot of people who had passed through Willow Garage at this point, moved on to startup robotic startups. I'll just put a link down here. I'll put it in the notes as well, to a nice set of videos from Red Hat about development at that point. It's a pretty professional set of videos about Willow Garage and what was being done there in the development of ROS. So after 2013, ownership of the open source software for ROS moved to Open Software Robotics Foundation. One of the things that they did was introduce ROS2 in 2016, because ROS1, or the initial version of ROS, had sort of grown organically at that point. There were some things that people knew could be improved, and I'll talk about some of the improvements that took place with ROS2. That's been going on for the last 4 or 5 years, but a really good stable version of ROS2 is the Foxy version, and that was released in 2020. And there's also a link again on the ROS.org page to the Foxy specific instance, or ROS2 instance. So let's have a look at ROS plumbing. So this is the piece that usually runs on the robot, and is the piece that manages the robot and the connectivity between things running on the robot. So it's made of 3 main things: nodes, topics, and messages. So nodes, they represent a piece of software, a frequently associated piece of hardware for a component of the robot. So maybe the base motor node is the node that manages the movement of the robot, so the wheels and the platform that the robot sits on. Things like the navigation node, so I talked earlier about some of the packages, so those are implemented usually as a package which is made up of 1 or more nodes. So there may be a navigation node that's used, but that may be a software only node. Camera nodes, so maybe interfacing with cameras, you use a camera node. Frequently you use a LiDAR node and computer vision node. And there's nodes for just about every piece of hardware that you would use on your robot, as well as software functions associated with the robot capabilities. So you have all these nodes, and these nodes can publish to and subscribe to topics, which I'm going to talk about in a sec. And the advantage of using this node approach is it breaks down the complexity of the robotic system. So people can just work on a specific node, can get that working properly, and then bring other nodes in that communicate with that node, which makes it easier than trying to work on the robotic system as a whole. Okay, the next ROS plumbing component is topics, and they're also called name buses. Topics is an easy way to think of them. It's a name for something that can be communicated over, subscribed to, or published to. So topics are set up so that nodes don't need to be aware of other nodes. They just talk to topics or listen to topics, and they can do that independently of other nodes. So it makes it easy to swap out nodes. Topics always have defined message types associated with them. So say you have a topic about, say, moving the robot base, there's a message type called command velocity message type, so that anything that wants to be aware of or respond to movements of the base can just listen for the topic, and they'll be able to interpret the command velocity message however their base works. So it makes them independent of the hardware. So some bases walk on legs, other bases have tracks or wheels to move the robot around, but they all want to do the same thing of moving the base a certain amount, and the standard command velocity topic can be read, or command velocity message can be read by all the nodes that are subscribing to that movement topic. And finally, as I said, there's the third component is messages, and these are the standard way of defining the messages that are used by topics. Typically when you're designing the robot, you can use these components to produce a ROS graph as well. So it's a simple way of architecting how the various nodes and topics and messages connect together. So if we look here, here's an example of a ROS graph. So this base serial is a node that manages the movement of the base for the robot in this case. It's doing things like publishing to a odometry topic. Odometry is information about where the robot is at the moment, and it's publishing to this odometry topic, and two things are subscribing to it. So this R tab map node, as well as this move base, which is part of a navigation routine. So navigation routine needs to know where the base is, so by tracking or subscribing to the odometry, they can keep track of that and keep updating the plan for how the robot gets from one place to another. I wanted to have a look at some examples of ROS robots that have developed using ROS out there. And for me, I'm in Philadelphia, so live close to a lot of giant food stores. And one of the things that they got a couple of years ago was this robot called Marty. It runs around in the aisles of the store, avoids people, seems to know where the aisles are, can run up and down the aisles. And its purpose is, at the moment, is just to look for hazards. So looking for where something's been spilt on the floor, or where there's something where it shouldn't be on the floor, where it could trip up a customer. And it reports back to the associates at Giant to clean things up or pick things up. This robot is developed by Badger Technology. I've put a link to them down here. So it's kind of a starting point at the moment, the way they use it. I don't think it's fully operational yet. But some of the things, when you look at the Badger Technology pages, that this Marty robot can do, is it can do shelf restocking. So it can run as it goes down the aisles. It should be able to look at the shelves, see if some of the shelves are getting empty, and let the people at Giant know that they need to restock some of the shelves. Can do price tags checks. So a lot of times there's sales on at grocery stores, so I can check that the tags on the shelves match up with the items and are current, so they haven't got items on sale that shouldn't be, or even that the items are lined up with the price tags they should be under. Does things like security, so either in a store or it could be in a warehouse environment. It can go around and just check simple things like, are windows open when they shouldn't be? Are doors open when they shouldn't be? Are fire extinguishers, in the right place in the warehouse or in the shop? Maybe in a hospital environment, it can check for things like defibrillators located where they should be, are in their cases and things. And finally, something they talk about is being able to do disinfection. So using a UV light attachment can go around and disinfect shelves. So for example, if customers go around and touch things on shelves, Marty can go around at night and just shine a UV light on those shelves to make sure everything's been disinfected, ready for the next day. Other uses I saw for ROS is NASA has been using ROS. So first time they used it big time was in 2011, between 2011 and 2016 on the ISIS space station. See example here. So what they did was put a fairly humanoid robot together. Initially it was just sent up to the space station, International Space Station, in 2011. Just the top part, the torso, didn't have the legs on it at that stage, and it was really to see whether a robot could be useful to help the astronauts. There's some routine tasks they do, and you'll see a link there to a YouTube video where it shows an example of this robot called ROS2, just checking simple things like air conditioning filters are working correctly. So sort of mundane tasks that the astronauts can do, just take that away from them, give them some more time to do other experiments. So they found they really needed to make this useful is to be able to have this robonaut move around the International Space Station. So I think it was 2014 they sent up these legs. So you see the lower part of the robot here in the photo. And the idea was the legs would allow the robot to move around the space station, grip things, and do tasks in different locations in the space station. The legs were designed after the robot was actually sent up, and this caused some problems. It required the astronauts to actually disassemble the robot a little bit, put the legs on, connect it all up again, and that did not go successfully. They had a lot of intermittent problems. I think they found out as a ground plane problem that they had in the end, but the end result was the robot wasn't really useful for use on the space station after that, so they brought it back down in 2016. Probably a more useful advanced use of the robot will be for this Viper lunar rover you see here. It's going to go to the moon in 2013. It's going to be a run round on the moon's pole, so it's going to be close to the top of the moon, and it's actually going to be looking for ice on the moon. So some of the particular problems with this mission is that for half the month where it's located on the moon is going to be out of contact with the Earth, so it has to run autonomously, and there's some challenges with where it is, where it's going to be difficult for it to stay in the sunlight all the time because of the rotation and the location is on the moon. So the robot needs to be able to move to stay in the sunlight to keep its solar cells charged. So they're going to be using ROS2 for this to give it a degree of autonomy. So I'll be interested in 2023 to see how successful they are with this, but there's probably a better use for ROS than trying to do the full humanoid robot thing on the space station. Some of the other things I've seen, this robot here you hear it advertised sometimes on podcasts. It's called the Gitter robot from Piaggio, which is an Italian company. They actually designed this in Massachusetts there. It uses ROS as well. So the idea with this robot, you see here, it's just a little like a cart that follows you around, so you can put things like groceries or your backpack in it. Probably useful more in the industrial environment, where maybe in a hospital you can put things in it just and have it follow someone around. It's just an easier way to carry things rather than always have to carry them yourself. I put a link here to a talk they had at one of the ROS cons where they actually use ROS, and they say in there that it's actually a lot faster to develop the software than the hardware, just because ROS had so many things in place, so they didn't have to reinvent too much to get this robot to be able to do navigation and follow someone around and do the things they wanted to do. But the hardware and the design turned out to take longer for them to do. And finally, just wanted to look at some robots, or example of robots that have used in education. So one of them is the TurtleBot 3, you see it here. So this is an evolution of the TurtleBot that was developed by Willow Garage. So it has some improvements over time. So the platforms on here are better, so you can attach more things. The idea with these educational bots is you want to be able to attach lots of sensors, have students try out different things, manipulation arms, all sorts of things. So this is a great platform for having the base platform that moves the robot around and having a place for putting lots of sensors on it and connecting them up. That's the TurtleBot 3. When Willow Garage was active, there was the PR2 we looked at earlier. They actually sold that as an independent product to educational universities and things as well. And finally, just have a look at one of these. So this is called Vector. I bought it a couple of years ago. So the company that produced it has actually gone out of business, but one thing it had was an API that you could code to, and people have done things like you see here. There's a GitHub repository for an interface to ROS for this robot. So even though the actual robot doesn't run ROS, it's very simple to put this in place and have it be a robot that is running ROS and communicating to the parts of the robot through the actual API. So finally, just wanted to have a look at ROS2. So like I said, when ROS was rolled out from Willow Garage to the Open Robotics Software Foundation, one of the things they wanted to do was, and this happened in 2016, is evolve ROS to ROS2, ROS1 to ROS2, because they knew they had some problems with ROS1. Had sort of been developed organically over time and really had a need to be rewritten, and they knew there were some obvious things they needed to change about ROS. So they developed a plan for putting ROS2 in place. Really the first usable versions of ROS2 really only came around in 2020, and some of the things they needed to do was migrate a lot of the ROS1 packages to ROS2 before it was a usable implementation. But I'd say after 2020, if you're developing a new robot and you don't have any dependency on ROS1, then you might as well do it in ROS2 because it is a better platform. Just a note too that ROS2 is not directly compatible with ROS1, but there has been a ROS1 to ROS2 bridge put in place. So if you have ROS1 components on your robot, or historically you've developed ROS1 components and must have it working with ROS2, then there are bridges out there that you can use. So some of the improvements that went into ROS2 is it now uses DDS, or Data Distribution Service, which is standard IP protocol for communicating between nodes, or acting as the transport over TCP/IP between the nodes. And this is much better than what was in ROS1. In ROS1 it was a custom protocol, and it required a special node called the ROS master to always be running, and all the nodes had to talk to the ROS master to be able to communicate to each other. By using this data distribution service, there's some big improvements. Things like now has a lot more interoperability, so you can even use DDS compliant components that aren't ROS2 components, and because DDS is a standard protocol, it's used in things other than just ROS as well. It's got improved interoperability. Again, it's a standard protocol, follows lots of standards, so is better for getting things working together. More reliability again, because it's being developed by the industry, used in a lot of things other than ROS. There's a lot of people have banged against it and made a much better protocol than ROS could do by just developing their own custom protocol. Better supportability again, because there's a large community of users of DDS, and there's improved security in it. Another big change in ROS2, in ROS1, the only languages that were supported for programming ROS was C++ and Python. And the APIs that each of those languages used were developed independently. So they did very similar things, but they didn't work exactly the same, which caused problems when you're developing something in C++ and tried to use it with the Python versions. Slightly different things could happen. So what they did when they rebuilt ROS from the ground up as ROS2, they made a standard API layer that all languages uses. So as well as C++ and Python using the standard API for ROS, it opened it up to a lot more languages. Now you see C#, the JVM, so Java programs, Swift, Node, Ada, Rust, have all been added as supported languages for ROS2. There's probably more out there as well, but just shows the benefit of having a standard API there. Another interesting thing with ROS2 is Intel went back and looked at how navigation was working in ROS1, and they saw, as navigation grew, there's a lot of common things that people wanted to do. So, for example, you need unique rule sets for navigation about how decisions are made about navigation depending on the environment the robot's running in. Before, you had to basically recreate the navigation node to take in each of these rule sets, but now they have a plugins capability for navigation where you can plug in different rule sets, as well as other things to do with navigation. So made it a lot more flexible and a lot easier to modify the navigation without basically having to rebuild it each time. And finally, for ROS2, they've improved the software quality, so they now use fairly standard software quality practices now, things like having test suites for ROS2, having standardized development patterns, and just saying that it's still not where it needs to be. So some of the big uses of ROS may be in things like autonomous driving in the automotive industry, or in healthcare, maybe for surgery or other healthcare functions. There's certain certifications that are associated with that software needs to follow, so even ROS2 doesn't have those certifications, so still a lot of heavy lifting needs to be done to make ROS2, as well as being better quality, to be able to be under an umbrella of the certifications that it needs to have to be used in different industries. So now I'll have a break and bring up some code windows and just show you some examples of using ROS2 in this case. First one's going to be showing you some basic demonstration of a TurtleSim application. So it shows you a simulation tool, as well as some of the topics and nodes, or examples of topics and nodes used in ROS. And then I'll have a look at some of the things I've been doing with ROS2. So I've been trying to develop a robot platform as well as a joystick that uses ROS. So I'll show you an example of what I've been doing there as well. Okay, for this first demo, I'm using demonstrating the TurtleSim package. This is on ROS2. So the windows I've got open here at the moment is I've got a SSH terminal going to Windows subsystem for Linux, which I've got ROS2 running on. I've actually got two windows connected in here. So the first thing I'm going to try, these are the commands I'm going to use here, is just do a node list. So this tells me any nodes that are currently running and shows nothing. We can also do a topic list, so same idea. I can see any topics that are open and available. So I see a couple of ROS outs is just the generic one for sending messages, and parameter events is used for managing parameters. Now the first thing I'm going to do is fire up this node. So the structure of this command is ROS2, all the ROS2 commands start with ROS2. I'm saying run, which means I'm going to run a node. This is the name of the package, TurtleSim, and then the name of the node is TurtleSim node. So this should fire up the TurtleSim node, which is a software-only node, and it's going to fire up an X Windows display of TurtleSim. So there's our little turtle in the middle there. Looks like it's going for a swim in the ocean. So the interesting thing now is if I do a ROS2 node list, I now see the TurtleSim nodes displayed in the list. I can also find out more about that node So this is all CLI commands for ROS2. So ROS2, I'm saying node, give me the information about the TurtleSim node. So it tells me all sorts of things, who's subscribed to it at the moment, what it's publishing to, and other things. So what this does is a simulator for a robot. In this case is this little TurtleBot. So the next thing I want to do is have a look at what topics are out here. So again, ROS2 is the command executable, and topic is the command. I want to get a list of what topics are out there, so we see all the topics, which are basically the ones that this node was publishing. So the next node I'm going to run, so there's another node I'm going to run, is called the TurtleBot key. And let's just clear the screen before I run that. Let's try it again. So it's the ROS2 again, to invoke the ROS2 commands, run, and the package in this case is still TurtleSim, and the node this time I'm running is TurtleBot key. So this is going to send publish to the topic that the TurtleSim is subscribed to. So I should be able to move the turtle based on this. So it's fired up, and you can see here on my keypad, if I move my keypad, messages are being sent there. So let's do one more thing. Open another window into this ROS environment, and I want to see, in this case, this TurtleBot key node is publishing to this topic turtle1 command velocity. Remember, command velocities are instructions to a base to tell it to move a certain amount. So if I start up this is going to show me any messages that are getting published to this topic. And now when I press the keys and look at the sim, so here that you can see down in this bottom window, it's showing the messages that have been sent to that topic. Which are messages are made up of telling it how far to move in linear directions, X, Y, and Z, and how much to turn. So when I move the left and right arrows, those are turn commands. Move the up and down arrows, those are linear commands, moving forward and back. Okay, the second demo may be a bit ambitious, but try and show things I've been doing with ROS, in this case ROS2, and some hardware. So I've developed a ROS2 joystick that sends twist commands, which are command velocity messages to anything that's in the same ROS2 system. And I've got a robot here, robot base with motors and things that are listening for those twist commands to tell it how to move. And also that robot base will send back odometry messages. So let's see if we can show everything working. So first the joystick control, so we can see it here. So that's got a Raspberry Pi inside it, and it's fired up a node automatically, and it's going to publish these base twist commands. So let's have a look at that if we can. Okay, so over here connected to the Raspberry Pi that's in this joystick box, and I'm going to do a ROS command to do a topic echo, so look at what messages have been sent by this topic, and the topic is bass twist. So if I click on that and move the joystick, you can see it moving, and it's sending the command velocity commands as we've seen before for both the linear and angular component of how the robot should move. At the moment the robot's not moving because I haven't fired it up. So I'm going to now fire up a second SSH instance, and I'm talking to the ROS2 instance that's in this Raspberry Pi on this mobile robot unit. And I'm going to start the base motor controller, which is the name of the node that controls the motors on this unit. So let's run that. So that's up and running. And now if I move the joystick, the robot's responding to that. The other thing I want to look at is, so this was sending those twist messages from the joystick, and the robot's returning it. This is just diagnostic messages, but let's open another window here. Again, talking to the Raspberry Pi on the robot, on the mobile robot. And this time I'm going to be looking at the odometer messages coming back from the robot. So we will use this ROS2 command, so a topic echo again, so subscribing to the topic, echoing what's been sent over that topic, and this time it's looking for the base poise messages, which is odometry messages from the base here. So if I hit that and so you see here, every time the robot stops moving, it sends one of these poise messages. And these are an interesting message. They're made up of both a point location and what's called a quaternion. I've never heard of those before. I probably can't even pronounce them. But that's an orientation message. So it's describing where the robot is in XYZ plane, as well as the orientation, or the yaw and the pitch of the robot in 3 dimensions as well. So where it's pointing at, and again these quaternions are really interested. I put a link in here. There's a lot of math YouTube topics on these, and there's a thing I'd never heard of, but it's kind of the next dimension in complex numbers. So you use the imaginary number I and 2-dimensional geometry, and for 3-dimensional this quaternion, which is a next number type for 3 dimensions. But that looks like it's working, and that's kind of where I am with the robotics and using ROS. I've got some work to do to get the LiDAR working that's sitting on top of the robot there, so I can start using some of the other packages like navigation and mapping for the robot, but I'll put the link into my YouTube series on this project, because there's a lot of videos out there about that. Finally, just some links, and again I'll put it in the description for this video as well. So for learning ROS, I did these two commands, two courses from Udemy, ROS1 for beginners, ROS2 for beginners. I found ROS1 was really good course. ROS2 kind of adds to that and gets you learning how to use ROS2. But good course is good. It didn't take too long to do. Again, the main ROS site is www.ros.org. There's a good list of packages out there for ROS, so if you're curious about all the capabilities and packages that have been written, if you go out here you see hundreds and hundreds of packages. You can do sorts on this too, refine it by the version of ROS that you're using, either ROS2 and getting down to the actual releases as well, like Foxy and things as well. So you can do quite a few sorts to find out if someone's already written capability that you would need for your robot. Again, link to that Red Hat series of videos about ROS. There's 6 of them. This is the first video here. And for my videos about ROS and developing this robot, and I'll continue to add to this list, is out on my Lupincorp site. This link here will take you to the video list on my site, or else there's a playlist out on YouTube for those same videos as well, so whichever way you want to get to them.